Reaction times can differ depending on many factors, and these factors can decide whether the time for reaction to occur is fast or slow. An example of a fast reaction would be the burning of a substance, and an example of a slow reaction would be the rotting of food. In this video, the four main factors that affect reaction rate will be explored, including temperature, concentration, surface area, and the presence of a catalyst. Before we do this though, let us explore how chemical reactions occur, and why some reaction rates differ from one another. To understand this process, collision theory can be introduced. Firstly, it is important to note that the definition of reaction rate is the speed of which a reaction is going, meaning it is how fast or slow the reaction is occurring. For a reaction to occur though, it must meet the standard requirements. Primarily, this means that the molecules must have sufficient energy to initiate the reaction, which is called activation energy, and the molecules must also have the proper orientation, meaning proper alignment with other molecules. This is the basic model of collision theory, showing that without these requirements, an effective collision will not occur. Collision theory is therefore linked to the rate of reaction, as it states that the rate of a reactant is proportional to the number of collisions between reactant molecules. Temperature, concentration, surface area, and the presence of a catalyst are the main factors that influence reaction rates, bringing us now to understand how each individual factor has an influence. Temperature is said to be proportional to the kinetic energy of the particles in a substance, meaning that at lower temperatures, particles have less energy than they do at higher temperatures. This therefore means that an increase in temperature of reaction results in a faster rate of reaction, showing an indirect relationship. This can be seen through an experimentally conducted example, where the same solutions of sodium thiosulfide and hydrochloric acid were reacted repeatedly, but at different temperature intervals, to see the change in reaction rates. As shown in the table, as temperature increased, the rate of reaction was faster, applying to what collision theory states. The increase in temperature increased the kinetic energy of particles, resulting in two ways. Firstly, this increases the frequency of particle collisions, leaving more particles to react with each other in less time. Secondly, a greater proportion of collisions have the energy required to react, increasing the chances of an effective collision. Now, another factor that affects reaction rate is the concentration of reactants. It is usually seen that by increasing concentration, the number of collisions between the reactant species increases as well, therefore increasing reaction rate. Now let's look at an example that can prove this. The reaction between magnesium and dilute hydrochloric acid shows that at different concentrations of the hydrochloric acid solution, magnesium reacts completely at different times. As shown in the table, at the highest concentration of 2 moles, the time taken for magnesium to react was only 3 minutes and 13 seconds, whereas with the lowest concentration of 0.5 moles, the reaction time increased to 16 minutes and 20 seconds. This clearly shows that as concentration increases, so does the reaction rate. This again can be explained through collision theory, as increasing the concentration of reactants increases the number of particles available to react. This increases the frequency of collisions between particles and leaves a higher percentage of successful collisions to result in a faster reaction rate. Now, surface area is another key factor that affects reaction rate. It can be explained through the difference between a large cube and the same cube but all crushed up. The surface area is the sum of the area of all sides of a solid, and in this case, all 6 sides of the cube. The surface area of the cube can be increased by dividing the cube into smaller pieces or crushing it into fine powder. This maximizes the surface area of the solid, increasing the reaction rate. A good example of this is between solid marble chips and dilute hydrochloric acid. In the orange balloon flask is crushed up marble chips with hydrochloric acid, and in the pink is the same but with non-crushed up marble chips. The solids were applied into the beaker at the same time using the balloons, and it was clearly visible that the orange one reacted more vigorously, completely reacting before the pink flask did. This can be explained again through collision theory, as increasing the surface area of solid reactants increases the number of particles exposed and available to react. This therefore increases the frequency of particle collisions and increases reaction rate. Now, the final factor examined that affects reaction rate is the presence of a catalyst. A catalyst is a substance which speeds up a reaction but isn't chemically changed at the end of a reaction.
Created using Powtoon.